Hello, hi, welcome. Welcome back to CS 700, Computer Science of Continuous Data Algorithmic Foundation of Numerics. So let us briefly recap the content of last session and then indicate our plan for today's lecture. So here we are. So last time we talked about notions of computability for single real numbers, and there were three natural notions which we then proved to be equivalent, but the equivalence came with a subtle issue, namely for proving equivalence, two binary encoding. So in order to be able to decide the binary expansion of a real number, we had to consider two cases separately. The first case, that the real number under consideration is actually a dyadic rational, in which case we were able to hard code that real number into an algorithm that decides the binary expansion. And the remaining case where the real number under consideration is not a dyadic rational. In particular, when we proved the binary expansion of a real number to be decidable, that proof did not give rise to a computational conversion. So we did not construct an algorithm that converts any algorithm computing a real number by means of approximations into another algorithm that decides the binary expansion. So in the sense of this meta-algorithm, converting algorithms for one problem into another, like reducing one problem to another, these problems were kind of different. This is like the decision problem whether for religious people whether God exists or not. So we constructed an algorithm, we constructed actually several algorithms and proved that these algorithms, some of these algorithms solve the problem, but we did not give a computational way of finding out which of these algorithms is the right one, similar to the decision problem whether God exists or not. One algorithm says yes and another algorithm says no, but this is not really helpful in actually finding out which of the two is the case. Similarly, our proof did not provide any assistance in finding out whether the given real number is a dyadic rational or not. And correspondingly, the algorithm deciding the binary expansion of that real number really must be chosen by us, by the mathematician, by the computer scientist, and cannot be selected in a hybrid sense. And the technical term for that is cannot be done uniformly in the real number under consideration. And we'll return to that issue when we talk about computing real functions and higher types. We also discussed examples of real numbers that are computable, closure properties of computable real numbers, and counterexamples, real numbers that are not computable. And a prototype such example, historically, the first explicit such construction is the limit of Specker sequence, which you can see here on the bottom of the slide. So Specker sequence is a sequence of rational numbers, which is computable in the sense that I'll expand on in a minute further. It's a non-decreasing sequence and it is bounded by one. So therefore, its limit, its supremum must exist, but by the very construction, its limit, its supremum has a binary expansion which encodes the halting problem, and therefore cannot be computable, cannot be decidable. Now you may say that this is an artificial case, and I agree it is, but nevertheless it demonstrates an important property. Whenever there's a limit involved, a naive mathematical limit in the sense of eventual convergence according to calculus, then there's a danger that the limit itself need not be computable. Or put differently, whenever we consider limits in proofs in calculus and want to convert that constructive proof into a computable computability statement, then uh, we have to be very careful, because in general such a limit can exceed the realm of computable real numbers. And for convenience, here's again the construction of the sequence, which involves the following integer functions. So it receives as argument the encoding, remember these brackets mean encoding, of an algorithm and an input to that algorithm, that the halting problem asks whether this algorithm on that input terminates or not. That's undecidable. But here we consider the function which assigns to that argument the number of steps that the algorithm makes on this input x. Now, if we could compute such a function, then we could also solve the halting problem, right? Because this number of steps is finite if and only if the algorithm A on input X does terminate. So in order to make this a total function, we've deliberately included a special non-natural number in its codomain, namely this symbol infinite. And this is exactly, so this function small t is necessarily uncomputable. And the trick in Specker sequences that kind of this uncomputability is pushed into this very limit, this infinity, into the, yeah, that's the limit of this series. That's the intuition behind the construction of Specker sequence. But we will return to this function several times in the course of this chapter 2 on qualitative real computability. Before maybe only in late October we will we'll be able to discuss real complexity. Okay, so and this Specker sequence is its limit, is uncomputable, but if we allow Oracle access to the halting problem, then it becomes computable. Then the binary expansion, of course, can be decided by, when given Oracle access to the halting problem can be decided, but then still the totality problem remains undecidable, because we established in chapter 1 on discrete computability that the totality problem is strictly hard, or strictly more undecidable than the halting problem. So even given Oracle access to the halting problem, where there are still undecidable discrete problems, and encoding these in binary into real numbers gives rise to real numbers which are still uncomputable relative with Oracle access to the halting problem. And in fact, an entire hierarchy of real numbers that has been introduced and studied, for instance, by Shizong Zheng, real counterpart to the discrete analytic hierarchy, arithmetical hierarchy of discrete decision problems. Right, so here for your convenience is the repetition reminder of our notion of Oracle computation, namely in terms of a while program, which can make subroutine calls to an arbitrary fixed, not necessarily computable total function. And in our case, we consider this function to be the characteristic function of the halting problem as a decision problem. So in general, this can be a function problem. And we've stated and indicated the proof sketch of a real version of the Schoenfeld limit lemma. The Schoenfeld limit lemma is about the discrete realm. A function from integers to integers is computable with Oracle access. to the halting problem if and only if it is the pointwise limit of a function without oracle access, but with an additional argument which tends to infinity, and the limit is considered pointwise with respect to that second argument tending to infinity. And this is an unconstrained limit, so eventual convergence within the discrete realm means it eventually becomes constant, independent of that argument, but eventually means exactly this. There's no explicit bound on how large that argument is sufficient to become, for the function to become stable in a sense. And similarly, the real limit lemma is, I think, much more natural because here we really have a limit in the sense of real numbers, not necessarily to become constant, but eventually to converge, really with respect to this second argument, j. And observe again, this is a limit without rate of convergence, and this is what corresponds to the oracle access to the halting problem, or put differently, from the perspective of numerics, where we had these notions approximating real number with error bounds and approximating real number without error bounds. In general, the difference in computability is as large as having oracle access to the halting problem and not having oracle access to the halting problem. And so that's a recap of last lecture, and our plan for today is to now proceed from computing single real numbers to computing real sequences as a little higher type object, right? So infinite countable sequence of single real numbers, and then to proceed up one step further to computing real functions. And we're going to introduce the notions, the definitions for both, what it means to compute a real sequence and a real function, and properties, in particular closure properties. These are the crucial criterion for justifying these notions to be as reasonable notions. Right. So here's the definition of what it means to compute a sequence of real numbers. So to compute a single real number means to produce approximations, dyadic approximations, integer numerator powers, integer powers of 2 as denominators to that real number with error bound 2 to the minus n. And computing a real sequence means doing the same, but now we have two inputs, the precision parameter n, which covers both the error bound and the denominator of the diintegrational approximation, and the sequence index j to the sequence. Which element of the sequence are we supposed to approximate in this sense? So this is the notion of what it means to compute a real sequence. And we're still going to look at some examples and counter examples of computable and uncomputable real sequences in this sense. But let's first state a property, a proposition, or a lemma, if you like, which will be useful and used repeatedly in the sequel, namely condition which does guarantee that the limit of a computable sequence is again computable, which, as you recall, which is not true for Specker sequence. So we really need an additional hypothesis. And the hypothesis here is that the sequence, well, necessary condition for a sequence to converge is, of course, that it must be a Cauchy sequence. And since the real numbers are complete, that's also a sufficient condition. So this is exactly what's stated here. One of several possible ways of quantitatively capturing qualitative property of being a Cauchy sequence, right? So all sufficiently large sequence elements are sufficiently close to each other, where this means sufficiently close. But now here, sufficiently close means error bound 2 to the minus j plus 2 to the minus I. And under this explicit quantitative notion of being sufficiently close to each other, then it follows that the limit is again a computable real number. And the proof of this proposition is actually not hard. So what is our hypothesis? We have an algorithm that computes the sequence in this sense. So given n and j, it outputs approximation to the j sequence element. And now let's consider an algorithm that only receives one single precision parameter n in order to compute the limit. And the algorithm we use is the algorithm that takes the simulates the given algorithm on input n, n. So that's kind of like a diagonal process, right? So we use n as precision parameter, and we consider the nth element in that sequence. Then it's easy to see following using that Cauchy property that the nth error 2 to the minus n approximation to the nth sequence element satisfies error bound approximates limit up to error 2 to the minus n plus 1, or put differently, twice the error we're supposed to attain according to this condition. So in the end, we better consider n plus 1 instead of n, and then we have the desired approximation to the actual limit, and therefore have obtained an algorithm which computes the limit real number. But let me emphasize that again, this really relies and depends on this explicit error bound of the approximation fast convergence sequence. Or put differently, for Specker sequence, which is a computable sequence in this sense, but it is a Cauchy sequence because it converges, but it is not a computable Cauchy sequence. Its rate of convergence is not computable in this sense and having error bounds. And another perspective on Specker sequence is the following. So we know, of course, that every sequence that converges classically in the sense of calculus must have a subsequence which converges fast in this sense, right? Which converges so that the approximations satisfy this explicit and strong error bound. But Specker's sequence indicates that in general, it is impossible to find such a subsequence. The subsequence that converges fast is not unique, of course. So I must say a subsequence, there are many such subsequences, but none of them can be computable in the sense according to Specker's example in general. Right? So whenever you see a proof in classical calculus that involves a limit, or that involves, in a sense, compactness, in the sense that choosing a converging or maybe even fast convergent subsequence, that's another case where extreme caution is required. Namely, such a subsequence exists, but finding it in a computable way in general may be impossible, as it is for Specker sequence. But the proposition, the way we will use it repeatedly in the sequel is whenever we have this computable Cauchy property, then the limit is again computable. So strengthening the classical hypothesis of Cauchy sequence, sequences converges if and only if it is Cauchy classically. Here we need to impose the additional hypothesis to make sure that the limit is also computable. And now, as I already announced, we're ready to talk about both examples and counterexamples of computable sequences. And a simple positive example of a computable sequence is 1 over j factorial, where j, as you remember, is the sequence index, right? That's a computable sequence. It's basically, you take the sequence j factorial, which is easy to compute. It's just an integer sequence. And then you take its multiplicative inverse, the reciproc, and then adopting our proof that the reciproc of a computable real number is again computable. Remember, every integer is also a computable real number. And so taking the reciprocal of a computable real number is again a computable real number. From that, it does not follow immediately that also the inverse of a computable real sequence is again a computable real sequence. But if you look at the proof, then in this specific case, it does hold. So this is an example of a computable sequence, and we're going to use that because this is, if you recall, the very sequence of coefficients to the exponential function's Taylor series. And later we will prove that the exponential function is computable, maps computable reals to computable reals. The crucial property will be that more generally, any analytic function with computable coefficient sequence is computable on a suitable domain subset of its radius of convergence. So that's why this sequence, we chose that here as a very simple first example. Here's an example of a non-computable real sequence, namely the characteristic function of the halting problem. This is an uncomputable sequence, which you may expect because it involves the halting problem, but the maybe more subtle and more interesting aspect and point is that here this sequence only attains value 0, 1, like any characteristic function, right? The values are only 0 and 1. And of course, these are computable real numbers. 0 is a computable real number and 1 is a computable real number. So that is to demonstrate that it is not sufficient for a computable sequence that all its entries are computable real numbers. This is a necessary condition. You see, any computable sequence has the property that any fixed entry of the sequence is a computable real number, but the converse is in general not true if we have a sequence of real numbers where every single entry is a computable real number. This does not necessarily imply that the entire sequence is computable, as illustrated with this example. This is a sequence where every entry is a computable real number, only 0 and 1, but the sequence in its entirety is not a computable sequence. Well, because there are two kinds of inputs. One is n, the approximation parameter, and also j, the sequence index. And here it is, in this example, it is j that makes the sequence uncomputable. The dependence on j, that's exactly what constitutes the halting problem. Whereas for Specker sequence, it's the dependence on n, the approximation error bound, that makes the sequence uncomputable. Here's another example, now again a positive example of a computable sequence. And this is a sequence that involves again our strange function t that let us recall for your benefit this definition of this function. This is the function that counts the number of steps that is made by the algorithm A on input X, both counted into one single natural number. So this is a function, integer function of one natural number parameter that counts the number of steps made before terminating, or that returns this special symbol infinity in case it does not terminate. And as I have to emphasize again, this function is of course not computable, right? That's the whole point. If we could compute it, that would mean we could solve the halting problem by distinguishing this special symbol from any other symbol. But in the way it is used in the construction of Specker sequence in such a subtle way that still the sequence is computable. And similarly, the way it is used here, sequence is still computable. And this is something I'd like and have to point out more explicitly. Why is this a computable sequence, although it is based on this uncomputable integer function? The reason is when the number of steps made on X is very large, is let's say larger than n, right? If the machine algorithm A on input X makes more than n steps, then it means that this function is value is larger than n. It could be infinite, but it's larger than n. But here the point is this is 1 over 2 to this function. So in this case, the value of this sequence element, the J sequence element, where J encodes the algorithm and its argument together into a single natural number, whenever this function has value greater than n and possibly infinite, then the value of the sequence element is less than 2 to the n, right? Less than 2 to the n, and therefore uh, can be approximated by 0, right? In either case, if it is the value is infinite, then 1 over 2 to the infinite is 0. So 0 is a possible value of that series, of that sequence element. Or if the number is finite but larger than n, then the value here is 2 to the minus some large number, but the number is at least n. So it is sufficiently close to 0 up to error 2 to the minus n, which, as you recall, is the very definition of computing this sequence. So in order to compute this sequence, here is a more or less explicit algorithm. Simulate the given algorithm A on the input X for n steps, a finite number, and if it terminates after, let's say, m steps less than n, then return 2 to the minus m, that number, and otherwise return 0. Whether or not it terminates, because even if it does terminate after finite number of steps, the value will be so close to 0 that it satisfies this error bounds. So put differently, putting this function here into the exponent, 1 over exponent, this kind of allows us to avoid deciding and distinguishing between when the value of this function is very large and when the value of this function is equal to infinity. In the discrete setting, we must, in order to compute this function, we must distinguish between both cases, but in the real setting, we can get around distinguishing them, and this is what makes this function computable. And we're going to recall this, use that later on this slide to really show that equality of real numbers is not just discouraged, as folklore says in numerics, but it is fundamentally impossible and independent of the representation of the real number. It has nothing really to do with using floating point numbers. It's an inherent property of real computation. Namely, observe that this sequence, which we've just established to be computable, the J sequence element is non-zero if and only if J is the encoding of an algorithm and input X which terminates. So put differently, the subset of those sequence indices whose element is non-zero, this is really equal to the halting problem as a set, because recall the halting problem is the set of all the such encoded pairs where this function t is strictly smaller than infinity, and this is exactly the same as saying that the sequence element is non-zero. It is 0 if and only if t attains the value infinity, if and only if this algorithm does not terminate on the input x. So we have really equality here as a set, and as I already announced, there's a converse to that. Namely, so recall that the halting problem is semi-decidable. It's undecidable, but at least it's semi-decidable. So that kind of means that in general, we cannot expect to decide equality of real numbers, regardless of how the real number is given. And this is a very strong uh, uh, statement which follows from this example, because here we're only dealing with a countably many possible real numbers, namely those that occur in the sequence. And those that occur in the sequence are here given by the sequence index j. So deciding this set means, given an integer j encoded in binary, tell me whether the j sequence element is 0 or not, and this is undecidable. This is a holding problem. So this statement basically means it doesn't really matter how the real number is given. Here it is only given by its index, which is a finite binary string encoding a natural number index. Then it is undecidable. And on the other hand, that's as bad as it can get. For every computable sequence, the set of indices, which are natural numbers, on which the sequence element is non-zero, that is always semi-decidable. So that basically means that testing real numbers for inequality is in general as bad, but never any worse than deciding the halting problem, which is at least semi-decidable, but not worse. And as I kept emphasizing, the interpretation of that statement means that the folklore advice in numerics, the gospel, avoid testing for equality, or rather don't test for equality, don't test for inequality. That is independent of the floating point representation. It's really an inherent property. In general, we can only test for inequality, and in general this will only be semi-decidable and not decidable. And so I've already indicated and sketched the proof of this to be a computable sequence. Now let me proceed to sketch the proof of the proposition that inequality is always semi-decidable, cannot get worse, cannot be, for instance, equivalent to the totality problem, which is more undecidable than the halting problem. And this is again based on this lemma, which we, if you recall, which we've used and discussed before when we established the decidability of the binary expansion of any computable real number. Namely, it is possible to semi-decide the first, or actually any fixed binary digit using this lemma, provided we're given a promise that there's no third case. The number must either be strictly smaller than 0 or strictly greater than 0. And this is right, it must be non-zero. It must not be a diagonal rational. And from this, it immediately follows that whether a sequence element is non-zero, that exactly means it is strictly smaller than 0 or strictly greater than 0. So by dovetail search for either this or this, we can semi-decide. We have an algorithm that terminates if and only if the sequence element under consideration is non-zero, right? And observe that this inequality here, these are two different kinds of inequality. Yeah, so this is a inequality between real numbers, with the real number r is strictly greater than the real number 0, whereas this inequality is inequality between integers, and of course equality between integers in binary representation that is decidable easily, right? So this is a different type of inequality than this, and same here, this is real inequality, this is integer inequality. Okay, so that's about some definition and some first properties of computable real sequences. And let's now move on to maybe interesting property of computable real sequence. Well, every computable real sequence is comprised of computable real numbers. As said before, every single element of the sequence must be a computable real number, but the converse is in general not true, as we discussed. Uh, but every computable sequence of real numbers, of course, contains only countably many real numbers, right? I mean, countably many computable real numbers. On the other hand, there are only countably many computable real numbers because there are only countably many algorithms, there are only countably infinitely many while programs. So that from this pure counting perspective, one could hope for a computable sequence of real numbers that enumerates all computable real numbers, precisely the computable real numbers, because it cannot have any uncomputable real number, right? But it turns out that this again is fundamentally impossible. Any computable sequence of real numbers must miss at least one computable real number. And this is the statement we want to prove here, because the proof is again a very nice and elegant example of diagonalization, similar to the diagonalization argument that we discussed when we established the undecidability of the halting problem following Turing's proof. So how does this work? So to remind you, this is the notion of what it means to compute a sequence, approximate, to compute a single real number means to approximate it up to error 2 to the minus n by the static rationals. And so by hypothesis, we have a computable sequence of real numbers, which means this. And so recall when we proved this proposition on the last slide, that the limit of a fast converging Cauchy sequence, fast convergent sequence of real numbers, computable sequence is again computable, then we would consider the diagonal sequence of approximations and prove that this approximates the limit of that real sequence. And here we're going to do the same, only we're considering the diagonal sequence of approximations, right? But with higher precision, not the precision n approximation to the nth real number in the sequence, but the precision 2n plus 1 approximation to the nth sequence and element. And the reason for this higher precision will become clear in a few minutes, but for now, I'd like to focus on the intuition. Of course, our goal is, as with any diagonal argument, to construct, to show that there exists a real number which is not contained in that sequence by diagonalization, much like Cantor's diagonal proof that there's no way to enumerate all real numbers. There's no way to enumerate all subsets of natural numbers by constructing such a subset which has been missed, deliberately kind of avoiding all those that occur in the hypothetically given sequence. And that's what we're going to do here. So we're going to define a sequence of nested intervals. So the nth interval will be a subset, actually a proper subset of the n minus first, and the n plus first will in turn be a subset of the nth, and so on. And this nested intervals, right? This means it's to be nested, will have strictly decreasing width. So the nth interval will have width 1 over n to the 3. And again, the choice of 3 will become apparent. There's lots of freedom here in this construction. But here we choose 1 over 3 to the n, so that this sequence of intervals actually converges to a singleton. And by converge, I mean the intersection of all these sequences is non-empty, obviously, right? Because every element interval is contained in the previous and so on. So by compactness, right? Remember, compactness means whenever we have a countable intersection of compact sets, then actually a finite intersection is already, if a countable intersection is empty, then already a finite intersection is empty. But here by construction, these compact intervals, every finitely many is just the final one, and which is non-empty because it has positive width. So that in the end, the intersection of all these intervals will consist of one single real number, and that's going to be the real number which is first missed by the sequence, and secondly still computable. So this will be the real computable real number missed by that sequence. Okay, so here's a picture that illustrates the intuition behind that construction. So let's say here's the n-1st interval, which we've already constructed as part of the induction hypothesis. And now we extend that to construct the nth interval, which is 1/3 the width of the previous interval. And to construct that nth interval, we consider the midpoint of that n-1st interval. Let's say this is a midpoint, and so the bounds of this interval will also all be rational numbers. Therefore, also the midpoint will be a rational number, and we compare that midpoint to the nth, right? So we proceed from n-1 to n induction step, the nth diagonal approximating sequence in this sense, which is another rational number. So here we have a rational number, and here we have a rational number. And as you recall, it is possible to compare two rational numbers. Difficulty comes when comparing real numbers. And so now comes our construction. If that rational number Qn is strictly greater or equal to this interval midpoint, then our next subinterval will be the first third of that previous interval, and thus indeed have width 1/3 to the n by induction hypothesis. This has width 1/3 to the n-1, so 1/3 will have width 1/3 to the n. And similarly or dually, if the rational number Qn, the approximation is less than this midpoint, then we consider this above interval point. If it is equal to that midpoint, then we choose either one. That doesn't really matter. Ties can be broken arbitrarily. The point is that here we're comparing rational numbers in order to define, inductively define the next smaller element of that strictly nested sequence of intervals of width 1/3 to the n. And the observation is that by this very construction, the nth real number in that computable sequence will not be contained in that nth subinterval. And why is that so? Well, because the nth element in that sequence is approximated by that rational number, very well approximated, because we choose error bound 2 to the 2n plus 1. So it must be very close around that rational number. And therefore, this interval around that rational number, where Rn is guaranteed to lie in, is disjoint from that subinterval here. And similarly, in the other case, when the rational approximation is strictly greater than here, that means that the real number Rn, which is approximated, is very close here, and then particularly is greater or equal to that midpoint. But in this case, remember, we considered this subinterval, which is disjoint to that. So again, the subintervals we construct by diagonalization are chosen such that this subinterval does not contain the nth subinterval does not contain the nth real number in that computable sequence. So, and as I mentioned before, the subintervals have an intersection that is a singleton, right? So their width tends to 0, so it cannot have a positive interval of positive length as in its intersection. And on the other hand, all the intervals are non-empty, so the intersection consists of precisely one real number. And this is the real number we are constructing as a counterexample, as a contradiction. This is the real number which will not be contained in that given sequence Rn. So this real number x is different. This differs from all the elements in that sequence because that's how we constructed it. That's how we constructed these subintervals so that the subinterval does not, each subinterval does not contain the nth subinterval does not contain the nth real number in that sequence, and therefore the intersection must be distinct, differ from all these real numbers. On the other hand, this is a computable real number because all this construction diagonal process is based on, depending on the comparison, whether this rational number is greater or smaller than this rational interval midpoint, which can be done computably. So by running the construction on an algorithmically gives rise to intervals in which constitute approximation to that real number, which is one of the definitions of that real number to be computable. Observe that here we do not use this definition of a real number to be computable, item B, but this is this item C, the third possible definitions, equivalent definitions for real number to be computable, namely can be approximated by rational numbers, which is basically the interval midpoint here, up to computable error bounds, and the error bound is here the width 1/3 to the n. So to summarize, every computable sequence of real numbers must miss at least one computable real numbers, and we've proved that by this very nice diagonalization argument. Good. So this is about counterexamples and closure properties of computable real sequences. And as I promised, today we also want to start talking about computing real functions. That's the next step up in the kind of type hierarchy. What does it mean to compute a real function? There are two perspectives of what is a real function. One is considering as a transformation. So a real function receives a real number argument and returns a real number value. So it's a transformation. And our definition that we consider here on this slide will turn that, or will require that this translation should be computable. Okay, and later we will consider other perspective of a real function as a kind of static object corresponding to maybe looking at the graph of the function, which is also a static object. And in classical calculus, we move back and forth between both perspectives. And here we're going to similarly investigate whether static definition of a real function and the dynamic one that we're introducing here are equivalent. So here's our dynamic definition of what it should mean for a real function to be computable. So to compute a real function should mean to be able to convert any real number argument x into a real value f of x, which we call here y. And but since both the argument and the value are real numbers, are infinite objects, we cannot compute them or process them as arguments in finite time. So instead, we current the definition of what it means to compute a real number, namely to output approximations to that real number. This is exactly what is written here, right? So output an infinite sequence of approximations, dyadic rational approximations with integer numerators and binary powers, integer powers of 2 as dominators up to error 2 to the minus n for any n, an entire sequence of such approximations to the value. That yeah, kind of picks up on this definition of what it means to compute a single real number. Here it means to compute a single real number, which is supposed to be the value of that function. So the difference between both, of course, is that a real function also has a real number argument, right? Whereas computing a single real number is an output-only process without input, well, except for the precision parameter. Compute a real number function also involves uh, uh, input, namely a real number. And here the definition requires the input, suppose the input to be given in exactly the same way as an infinite sequence of numerators to diagonal approximations up to error 2 to the minus m for arguments in the domain. And I'd like to emphasize here that for maximum generality, we're going to consider partial functions as is indicated by this symbol. So the function need not be defined, not necessarily for all possible real number arguments, but when it is defined, when we have a real number argument that does belong to the domain, and when we have uh, this argument, infinite real number argument, given by an infinite sequence of approximations that all satisfy this error bound, then the machine must output a similar sequence here. So, and yes, I keep emphasizing that there are several subtleties to this definition. The first subtlety is the input now consists of an infinite sequence of integers, let's say encoded in binary. How do we input an infinite sequence of integers? For instance, on a Turing machine, one would spell them out on a tape, or call that Turing machine tapes, or, well, some people call them unbounded, or could also say they're infinite to begin with. So this is basically just the same as a Turing machine model, an infinite sequence of inputs. But of course, in order to output a similar infinite sequence of approximations for the value, we cannot expect an algorithm to first read the entire input before starting to produce output. This is very different from the classical discrete setting where the input is finite, so it can be read before starting to process or to even produce output. Here, the input is infinite, so it must start, the computation must start producing output approximations when having seen or been able to process only finite part of the infinite input. So that's the first thing I need to emphasize here. The second thing I want to emphasize is that the requirement here is only whenever the argument, real argument x belongs to the domain of the function, and whenever the approximations to that real number satisfy this condition, then the computation is supposed to do something. When this hypothesis on the argument fails, is violated, then there's no requirement at all. Then still the computation can output some infinite sequence. It could also output some finite sequence and terminate, or it could output any garbage. We only impose conditions for arguments that satisfy this condition. And the reason will become clear soon when we discuss the closure properties of this notion, which are much better when we do not impose any condition on the behavior of the computation when the argument lies outside of the domain. Also, this approximation condition cannot even be checked in finite time because it must be satisfied for all m, for all infinitely many choices of natural number m, right? So we cannot simply change the computation to verify that condition, and only once it's verified, confirmed, start computing, because confirming that condition would take infinite time, as would reading the entire input, which is impossible. So the computation is allowed, is in general will behave arbitrarily, both when the argument lies outside of the domain, and when some approximation property is violated, then can behave arbitrarily. And as I said, this notion has been crafted and over literally over decades since Turing, mostly by Klaus Weyrauch, who also initially considered other notions with required behavior for arguments outside of the domain, but uh, by requiring such behavior for arguments outside of the domain, several of the closure properties would be violated. So with this definition, for example, we have one nice closure property, namely whenever we have a computable partial function and a computable sequence in the sense of the previous slide, computable sequence inside of the domain, which we cannot verify, but need to be promised to be true. If both are computable, the function and the sequence, then the sequence of values is again a computable sequence. So this is one of the nice closure properties. Plug in a computable sequence of real numbers into a computable function, and the result will again be a computable sequence. And that's actually easy to show. Maybe you will turn that into homework, next homework. Another good closure property is computable functions are closed under composition. And again, I cannot overemphasize the importance of that property. This is basically closure under composition is what underlies all modular software development, where some group may develop one module and another group develops another software module, and then by closure under composition, one can combine both. One module can call the other or vice versa. So this is a very nice property. And in particular, this property really crucially depends on both input and output to be given by approximation. If we, for instance, suppose only the output, the value to be given, to be approximated by the argument, maybe restrict to rational or diagram numbers to be given exactly, then there's no closure under composition. We cannot convert the approximate output back to exact input for the next part of the computation in general. So this same treatment of approximations for both input and output, this is essentially what asserts closure under composition of the computable functions. And the third property is that any restriction of a computable function is again computable. So any restriction really, we don't need to have any, there's no requirement, no hypothesis on the domain of the partial function under consideration. And that's exactly because of this property that we don't require any behavior for arguments outside of the domain. So if we restrict the function, then we can still use the same algorithm computing that function. It will still produce the same output as before the restriction, but no, we just don't care about the behavior of that computation. We only care about what it does on the restricted domain. So to summarize, this is our notion of computing real function, and it is based on the transformation philosophy of a real function as transforming real arguments to real values, and it gives rise to these very nice three closure properties. And so, right, it's about computing real function. Let's now talk about examples and counterexamples. And an important property is of computable real functions is, and yeah, don't be surprised, any computable real function is necessarily continuous. And while people in numerics, for instance, are happy to follow up on this this definition and the closure properties, this is where I often start to sense disagreement but it's a consequence of that definition. And we'll discuss after this proof ways of avoiding this. So one common way of avoiding is this requirement. It's a strong requirement, right? The sine function is uncomputable, for instance, the signum function, right? Because it's discontinuous. And one way to avoid that is by requiring, for instance, the argument to be given exactly. But as I kept pointing out, then we cannot expect closure under composition. If the argument is given exactly and the value is given approximate, there's no closure under composition. If both argument and value are supposed to be given exactly, then we cannot have transcendental values. So the exponential function, for instance, will be uncomputable in this setting. So there's, I mean, they're all advantages and different disadvantages to different definitions. We're talking here about what is the right or good definition to compute a real function. Then there are many variants of this, but all the variants have different trade-offs and disadvantages. And in this lecture, following computable analysis, decades of investigations in computable analysis, this seems like the one of the optimal trade-offs, in particular having all these nice closure properties. The disadvantage is that discontinuous functions cannot be computable. And let me sketch the proof, not in a formal way, but by on its intuitive level proof sketch by demonstrating that, for instance, this discontinuous function is uncomputable, and from that it will be, you will have no difficulty in generalizing and formalizing the proof to any discontinuous function. Okay, so it's going to be a proof by contradiction that this prototype or example function is not computable due to this discontinuity to the jump of real values from here to here. So here we have an open, this point is not part of the value, this point is part of the value. The other cases where it's converse the other way around, it can be treated similarly. There's nothing really to add and insight from other cases. You can do that as a homework or exercise. So let's suppose there's an algorithm which computes this discontinuous function, and in particular, when given approximations to the argument x at the very discontinuity, right? X we use here for x to denote the discontinuity, which can be an arbitrary real number, not necessarily dyadic rational or not even a computable one. But by hypothesis, the algorithm receives as argument dyadic rational approximations to that real number, or put differently, it receives these intervals of width 2 to the minus m, so decreasing width, and must output similar approximations, similar intervals for the value f of x. And I'd like to emphasize that the definition of what it means to compute a real function makes no hypothesis, no condition on that there be a one-to-one correspondence between the single elements of the input sequence of approximations and the output sequence of approximation. It could, for instance, happen that the algorithm now needs reach the next input approximation, a smaller interval, and outputs another approximation, reach another input approximation, and so on, or could first read several input approximations before producing the next output approximation. There's no correspondence, explicit correspondence required for in this definition, which is another perhaps subtle but important point underlying this definition. This is basically what makes this definition differ from domain theory. Domain theory more generally requires that input intervals, every single input interval is mapped to an output interval. So their domain theoretic definition of what it means to compute a real function is really input an interval, output an interval, input a beta interval, output a beta interval, and so on. One-to-one correspondence between intervals. The definition we use here in computable analysis, which one can prove to be equivalent for functions, but which Matthias Schröder proved to be non-equivalent for higher types in general, removes that one-to-one correspondence between input approximation and output approximation. But let's return to the proof that any computable function must be continuous. So eventually, the output approximations must become better than the height of this jump of the discontinuity, right? So like in this case, all the output approximations must contain the actual value of the function. That's the condition here. And also the output approximation error must become smaller and smaller. So eventually it will be, at some point, it will be really smaller than the height of the jump of the discontinuity. Now we're going to play adversary. We're going to fool this hypothetical computation in a similar way that we fooled a hypothetical algorithm solving the halting problem at our first chapter to prove the halting problem. Undecidable, similarly, we're going to fool, act as an adversary, fool the hypothetical computation of this discontinuous function. Namely, now we're going to restart this computation. It's a deterministic while program, right? We didn't even discuss non-deterministic while programs at this stage. So when we restart it again with the same input, it will produce the same output. But now we're going to restart the computation with our goal in mind for evaluating the function at this argument x prime, not at the discontinuity, but at an argument which is slightly off the discontinuity, so slightly that it is still lies in the interval that the computation has read for its approximations. So this is kind of crucial, because when we now restart the computation, it means that we, as the user, can reuse the same approximations for the argument x, but now, of course, we use them as approximation to our new argument x prime. That, of course, works only for finitely many steps. Eventually, the interval will not contain, we'll have to distinguish between x and x prime. But for now, we restart the computation and look at what the computation will produce as output approximation. Since so far it only sees the same input interval approximations as in our previous execution, it will deterministically also produce the same output approximation as previously. And in particular, it will eventually output an output approximation which does not contain the value of this discontinuous function at the new argument x prime, because this is beyond the discontinuity, right? So previously it was this value, and now it should be approximation to this value. But what the computation does, it outputs the same approximation intervals again, which does not contain this value. And this is a contradiction. The computation does not work correctly. We have fooled it. That was our purpose. We've deliberately chosen another argument x prime, which is slightly off from the discontinuity, but which still lies in all the intervals that we used before, finitely many intervals for our previous execution, for our previous computation. So the computation thus produces incorrect output, which violates the output error bound here, which is a contradiction to the hypothesis that this computation, or that there exists a computation which computes this function with its discontinuity. And I'll leave it to you to generalize that proof sketch to any other discontinuous function any other discontinuous function can similarly be shown uncomputable. And right. Yes. So let's leave it at that. Any computable function is necessarily continuous according to this proof sketch. And we will later discuss ways of how to circumvent that condition. And there will be two approaches to achieve that. One is to consider multifunctions, which are in a sense non-extensional functions. And the other approach will be to add discrete data to the continuous argument like x here. But let's leave that for later, for part of that lecture. So time is already running up. So let's recall and wrap up today's lecture. So we've recalled what it means for real number to be computable, and then we generalize that to the definition of a computable real sequence. And we've discussed properties of computable real sequences. And one nice, and we've discussed examples. So for instance, Specker sequences and the sequence of coefficients to a power series of analytic function, like 1 over j factorial, the coefficient sequence for the Taylor expansion of the exponential function. We've seen that the characteristic sequence of the halting problem, although it consists only of computable real numbers, is not computable as a real sequence. And we've seen this example sequence, which kind of converges to the characteristic function of the halting problem, which is a computable real sequence. But the set of indices where the sequence elements are non-zero is equal as a set to the halting problem, which gave rise to this formal justification that indeed inequality of real numbers is in general semi-decidable, but no worse than semi-decidable. Then we proved that every computable real sequence must necessarily miss some computable real number. It cannot include all possible computable real numbers, although it only consists of computable real numbers. And then we've discussed the notion of what it means to compute a real function based on the transformation perspective, transforming sequence of our approximations to the real argument x to a sequence of approximation to the value f of x. And we've seen that this notion has nice closure properties with some subtleties involved, like not requiring any particular behavior for arguments outside of the domain. And we've just seen that any real function which is computable in this sense must necessarily be continuous. And for continuous functions, as you recall, any continuous function in a compact domain is uniformly continuous, and according to Weierstrass approximation theorem can be approximated by polynomials. And on the next slide, we will discuss this Weierstrass approximation theorem from the computability perspective. Namely, it will turn out that an equivalent characterization of computable real functions in terms of approximations by Weierstrass polynomials, that is, by a computation which only produces output, which is kind of the static perspective of looking at a real function as a static object, looking at its graph. And they will then prove that this is equivalent, which again, as you recall, if we have two different definitions that turn out to be equivalent, that's strong evidence for this definition to be reasonable. And that's all for today. And yeah, thanks for your attention. Thanks for listening. And see you again on Thursday when we discuss the computable version of the Weierstrass approximation theorem. Bye.